the talk here, in-person talk. Dr. HooYoung An, she received her degree in the School of Computing from the Korea Advanced Institute of Science and Technology, KAIST region in Korea in 2016. She is currently a PI with the Supercomputing System Research Section at ETRI. Her research interests include distributed and parallel computing, AI, and high-performance computing. She has been here in the earlier years as speaker. So today she will be sharing the very latest things. I think there have been some questions about the CXL and all. So her group has been working on this collective communication software for heterogeneous AI accelerators and CXL-enabled systems. And from the MAPIS group also, we are working for the last 2-3 years, trying to see if the CXL actually provides high performance communication, how we can enhance the MAPIS collectives. Okay, so that is the project we have been working on. So let Dr. An start. Okay.
Hi everyone, my name is HooYoung An. I'm a principal researcher at ETRI. I worked in the Networked AI Computing Research section in AI Data Center Research Division. First of all, I'd like to thank Professor Pender for inviting me to MOOC as a speaker and for giving me the opportunity to introduce the research we are doing in Korea.
Microphone.
My name is.
Is
it okay? Okay. So, today I'd like to talk about the collective communication software optimization for heterogeneous AI accelerators and CXL-enabled systems. This talk has 2 parts. Part 1 is collective communication software optimization for AI accelerators, and part 2 is CXL-based collective communication. Let us start with part 1. The title of this project is Collective Communication Software Optimization for AI Accelerators. This is a national research project funded by the Korean government. ETRI is the project leader, and we are working with 2 Korean chip companies, HyperXL, a Korean NPU company, and MangoBoost, a Korean DPU company. This is a 5-year research project from April 2026 through 2030. And the goal of this research is to develop a vendor-neutral collective communication library called KCCL that supports K-AI accelerators, as well as NPUs, PIMs, DPUs, and other AI accelerators. AI models and AI users are growing explosively, and so we need much larger cloud system built on AI accelerators. Cloud systems are moving from GPU-centric designs to integrate heterogeneous AI accelerator systems. The AI accelerators are semiconductors designed for high-speed, high-efficiency AI training and inference. The Korean government and industry are joining forces to build globally competitive next-generation AI accelerators. Korea developed NPUs, PIMs, and DPUs. The hyperscale AI models runs across computing nodes and accelerators using TP, PP, and EP. It is partitioned once, and then the nodes frequently communicate to synchronize data. So the communication becomes the bottleneck, and AI accelerator utilization is degraded. The collective communication is a communication pattern where group of accelerators exchanges, combines, and share data. This figure shows an example of a reduce running on a large-scale cloud system equipped with AI accelerators. Each node has a partial sum, and after all reduce, every node has the total sum. Or reduce, scatter, or gather, scatter, and gathers are the representative collective communication patterns. So we need high-performance collective communication software to relieve these bottlenecks. And there are two types of CCL software. One is the MPI-based CCL, and the other is the vendor-specific CCL. MPI-based CCL supports heterogeneous systems and large-scale clusters, and it covers full distributed communication, including P2P. The vendor-specific CCL is optimized for a single vendor's accelerators, and it provides low latency, high bandwidth by utilizing the hardware architecture. And I will summarize the vendor-specific CCL trends. Globally, this vendor's software stack can lead to the vendor logging problem. And there is no general purpose CCL that works across heterogeneous AI accelerators. In South Korea, the current R&D project focuses mainly on per chip performance, and multi-MPU support works only within a node. However, the heterogeneity across MPU, PIM, and DPU product is rapidly growing. Currently, there is no collective communication software that integrates and optimizes South Korean AI accelerators. So these problems cause four specific problems: low performance, low scalability, low resource utilization, and vendor lock-in. So we propose KCCL, a collective communication optimization software for South Korean AI accelerators. We aim to achieve high performance, high scalability, maximize the utilization, and vendor neutrality through this software. H3 is the leader institution, and HyperXL, a South Korean MPU vendor, and MangoBoost, a South Korean DPU vendor, are the core research institute. H3 is in charge of vendor neutral architecture, baseline source code, open source release, and overall project management. And HyperXL is in charge of KMPU, KPIM SDK, intranode communication optimization technologies, and KMPU, KDPU RDMA support. MangoBoost is in charge of KDPU SDK, internode communication optimization, KMPU DPU RDMA implementation. So we designed a plug-in based vendor neutral CCL architecture to support AI accelerators from multiple vendors. The green boxes are components for high performance, and the blue boxes are components for high scalability. The orange box is component for resource efficiency, and the yellow boxes are components for vendor neutrality. In the hardware layer, there are accelerators from various vendors, including KMPU, KPIM, KDPU, and third-party AI accelerators. In the application software layer, the AI frameworks such as PyTorch and VLLM utilize the KCCL as their communication backend. And the AI services running on those frameworks can provide high-quality services to users. And the KCCL consists of 4 layers. The layer 1 provides SDKs for AI accelerators. The layer 2 provides CCL frameworks and plugin functions. And the layer 3 provides CCL core functions, including common functions and programming model, intranode and internode communication technologies, MPU-driven networking technology, and AI framework integration functionalities. And the layer 4 provides AI workload-aware CCL optimization technologies. So we have three research outputs: KMPU, KPIM SDK, KDPU SDK, and KCCL. To achieve this goal, we derive 6 research topics, and each topic will be explained from the next page. Topic 1 is the resource utilization maximization technology. This is the collective communication technology for jointly optimization of data movement, computation, and synchronization across K-AI accelerators. In the conventional accelerator-specific communication, the collective communication across heterogeneous K-AI accelerators is not possible. As a result, the resource efficiency and system performance goes down. However, in the proposed accelerator unified collective communication, the unified CCL execution across heterogeneous AI accelerators will be possible with the CCL level optimization. And HyperXL has started to developing a PIM integrated MPU device in Korea. As a result, the resource efficiency and system performance goes up. The research topic 2 is vendor-neutral collective communication technology. This is the collective communication technology based on CCL framework and plug-in architecture. In the conventional vendor-dependent collective communication, the vendor-dependent runtime and SDKs, there is a vendor-dependent runtime and CCL software stack. And CCL software re-implementation required for new types of accelerator. As a result, closed vendor ecosystem limits the AI infrastructure scalability. In the proposed vendor-neutral collective communication, vendor-neutral runtime and CCL software is provided. No CCL software re-implementation required for new accelerators. This is because the hardware abstraction will be provided by the CCL framework and plug-in architecture in this layer. As a result, open vendor ecosystem improves the AI infrastructure scalability. The research topic 3 is device-driven collective communication technology. This is the collective communication optimization technology that removes CPU-centric bottlenecks for intra and internode communication. In the conventional CPU-driven communication, CPU generates collective commands and manages device state in the intranode communication. And there are many buffer copies through CPU memory in the internode communication. As a result, the host overhead and communication latency goes up. In the proposed device-driven communication, devices generate collective commands and manage device state in intranode communication. And there are no buffer copies through CPU memory in the internode communication. As a result, the host overhead and communication latency goes down. The research topic 4 is PIM-based CCL acceleration technology. This is the collective operation offloading technology using PIM to minimize data movement. In the conventional MPU-based collective communication, collective operations cause frequent data movement between DRAM and MPU processors. So large data transfers are required for simple MPI reduction operations. So the high-performance MPU processing units should be utilized for simple reductions. As a result, the latency and power consumption goes up and the system efficiency goes down. In the proposed MPU PIM-based collective communication, the collective operations no longer cause data movement between DRAM and MPU processors, since the reduction can be run inside the DRAM PIM. So small data transfers are required for simple reductions, and the high-performance MPU processing units can be utilized for AI inference job. As a result, the latency and power consumption goes down and system efficiency goes up. The research topic 5 is P2P RDMA technology between DPU and NPUs. This is the direct internode communication technology using KDPUs. In the conventional host memory-based RDMA communication, indirect data transfer is performed between NIC and NPU. And PCI bandwidth is wasted for this communication. So the host overhead and latency goes up and bandwidth goes down. In the proposed direct NPU DPU P2P RDMA communication, direct data transfer is performed between NIC and NPU. And the PCI bandwidth is not wasted. As a result, host overhead and latency goes down and bandwidth efficiency can go up. And this technology will be designed and implemented to be compatible with the standard RDMA software stack. And topic 6 is the network congestion control technology. This is the internode communication optimization technology based on UEC standard. The conventional static network control approach support only fixed congestion control and fixed path routing. As a result, the network utilization goes down and the latency goes up. However, the proposed dynamic network control approach will support the dynamic congestion control and multipath routing with packet spraying in the KDPU. So the network utilization can go up and latency go down. This is the conclusion of our first part. The Korean government has launched the development of KCCL, a collective communication software that supports not only K accelerators, but also third-party accelerators. We have just begun this 5-year journey for KCCL, and we look forward to your interest and support. Now, let us start with the part 2. The project title is Enhancing MPI Collective Communication Performance using CXL Shared Memory and Intelligent CXL Switch. This is the joint research between HooYoung and OSU. And this project was carried out over 2 years from September 2023 through August 2025. The goal of this research is to improve the MPI internode collective communication performance in a multi-node environment connected by CXL. So HooYoung focused on single rack scale CXL memory pool and intelligent CXL switch. The OSU focused on beyond the rack scale CXL memory pool. In a traditional rack, using Ethernet and InfiniBand, the communication latency between processors running on multi-node is 2 to 4 and 1 microsecond respectively. However, in a CXL 3.1 enabled rack, then latency can be reduced to 300 to 400 nanoseconds by using the CXL shared memory pool device. So in this research, we proposed IMAX, which is intelligent CXL-based memory expander. The OLIDUS is the representative collective communication utilized in data-intensive AI applications of AI and HPC field. In the conventional architecture, the computing nodes are connected via the network switch, and the MPI ranks running on different computing nodes perform pairwise communication, and the number of communication becomes n squared, and the communication latency is 2 to 4 microseconds. And the MPI computation is performed on CPU, and the number of communication is n. And the main memory utilization is low because not all the main memory is utilized during the runtime. We solve those problems by proposing the intelligent CXL switch, IMAX. IMAX consists of CXL memory pool manager, MPI computation accelerator, and MBAPIC to optimize for IMAX. In this architecture, the number of computation becomes n, and the communication latency becomes 300 to 400 nanoseconds. And the MPI computation can be performed on this dedicated accelerator, and the number of computation reduced. And the main memory utilization becomes high. And we design and implement the IMAX CXL switch, which consists of MPI operation accelerator. And we implement the reduce scatter and all reduce utilizing the IMAX. We can expect the performance improvement by reducing the number of communications and the CPU overhead by offloading MPI computation to the IMAX CXL switch accelerator. And we designed the offloading and result packet structures for the IMAX CXL switch, and we extend the MBAPIC 2.3.7 to leverage the IMAX CXL switch. And this result was accepted at IEEE Cluster 2026 and will be presented next month. This figure shows the IMAX-based collective communication accelerator. And this CXL switch, and this is the CXL switch layer, and this accelerator is used for MPI operations. So this is the conclusion of part 2. We improved memory utilization for AI and HPC systems by using the CXL memory pool, and we enhanced the collective communication performance with the MPI accelerator in the IMAX CXL switch. And through these two approaches, we developed technologies that contribute to improving the performance of AI and HPC applications. So thank you for your attention, and please feel free to ask any questions.
Let's thank the speaker. Do we have any question for Dr. An? Yes.
Thank you, and nice talk. My question is, what is the scale of the kind of CXL-based collective?
We utilize the CXL-based system as a software emulator, and we assume the singlet having 8 to 16 computing nodes. And we had experiment our proposed approaches on that system, and we can get good numbers.
Okay, yeah, thank you. And I think that's the scale for a single CXL switch.
Yeah.
Is it possible to aggregate those switches together to get better performance or scale?
We also consider that beyond the leg scale approach, and that was the research item of OSU, and we put together the idea and plan to submit that research to.
Okay, thank you. Thank you very much.
Any other questions for Dr. An? If not, in the interest of keeping us on time, let's thank the speaker again.